Hello everybody, and welcome to the Winter Colloquium from the Young Scientists Association of the Medical University of Vienna with the topical subject Machine Learning in Medical Science, which I'm pleased to moderate together with my colleague Philip. And it almost became a tradition to host a YSA COVID remote event. It is the second one. However, during these crazy times, we are more than happy to still have the opportunity to welcome 3 international speakers today who will talk about the latest techniques and applications of machine learning in medical science.
Thank you very much. A warm welcome also from my side. I can only agree with Melanie. We are more than grateful to host such wonderful speakers today with their talks and afterwards discussions. Machine learning as a subfield in artificial intelligence has become more and more important in recent years in biomedical research and also in medical sciences. It is still constantly gaining at importance too. It even helps providing solutions for problems that were previously considered unsolvable. We are therefore very excited to see what developments await us at the forefront of this very exciting field.
Well, then I would like to start and introduce our first speaker, Fons van de Sommen, who is an assistant professor at the research group Video Coding and Architectures of the Department of Eindhoven Electrical Engineering at the Eindhoven University of Technology. Welcome, Fons van der Sommen, and the stage is yours.
Thanks a lot. Can you all hear and see me?
Yes.
Obviously, I'm still in my son's room due to COVID, so now I'm trying to share my slides. Let me see if that works. If I switch to presenters mode, can you now see it in presenters mode?
Yes.
Looks good, yeah.
Okay, well, thanks for inviting me. I'm going to give a brief talk of some of the work we do. It is, but probably most of you will know. Then I'm going to tell you where we stand, and then I'm going to move beyond the visible. So what I mean by that you will see in a bit. So first, a bit about our research cluster. So these are all PhD students working in my cluster. So I get to present the nice stuff that we do, but I'm definitely not the one that achieves it all by himself. So these faces are helping me and helping us to get these nice results. So basically what we work on is computer vision and artificial intelligence for medical imaging to help medical doctors make good decisions. So we work on image and video processing, computer-aided detection and computer-aided diagnosis, but also image quality assessment and, for instance, denoising. So maybe we can use less dose when we're making an X-ray image. Some of the research themes that we dive into are the neural network architectures. Can we do it a bit more efficient or maybe a bit faster? Unsupervised learning, especially in medical imaging, it's hard to acquire data with labels. And my own background is in signal processing, so I try to use some of those techniques to even make these networks better than you would if you only use computer science. So some of the current challenges, and I think this is very generic, that I see in my work and see in the field is data. It's very hard to acquire large representative data sets, especially to have them labeled. If you want to have medical doctors label all your data, that's very expensive, of course. Sometimes you deal with privacy issues. And fortunately, some of the diseases that you work on are occurring not that much, fortunately, but then you also don't have sufficient data maybe to train your network. Then uncertainty, I think, is a very important topic that we like to work on, because if you ask a couple of doctors to annotate a single image, they can come up with different answers, right? There's a huge inter-observer variability in medical imaging. In contrast to my colleagues working on automotive, if they want to annotate a car, you get like 10 times the same answer from 10 different people. But in, for instance, annotating cancer in a radiology image, that can be, there can be much more uncertainty there. Then efficiency, we see also that a lot of the networks that you see being used are very large and very slow and not memory efficient as well. So this is really a theme. If you want to have your machine learning model implemented in clinical practice on the hardware that's available in a hospital room, you want to also do it a bit more efficient. Robustness, so this is an interesting one that I will come back at later. If you come from a mathematical background like myself, then we like to have models that you can at least say that they show some stable behavior for all possible input. But if you work with machine learning, then you see often that you cannot guarantee the stability for all types of input. And this is as trivial as using a different device or a different manufacturer. So maybe you have a Philips scanner and now you're going to deploy your model for a Siemens scanner. Then you can get weird results if you don't take care of this. So this is increasingly important, especially in the medical domain. And then one more very important aspect is interpretability. So what's actually happening inside these huge networks? So can we see how the stream of information is flowing, and can we do it more efficient? And also something that's related is explainability. So how can we communicate the results of a model with humans? So these are all topics that I work on with my cluster. Unfortunately, I cannot address all of them, but I'd be happy to discuss them with you later in the discussion session. So some of the research application. So for instance, one of my PhD students is working on denoising dual energy CT scans for detecting brain stroke. And yeah, then for instance, you have having a dual energy scan, you can do sort of a color X-ray image where you can differentiate between different materials, for instance, between white matter, gray matter, and blood. And that can be very interesting if you want to do stroke detection. Another project is on pancreatic cancer, where we try to segment all the interesting structures and find pancreatic tumors, because there it's very important for making a decision whether you can do surgery on a patient or not, what the location of the tumor is with respect to the local vessel structure. Another interesting project that we work on is colorectal cancer, so classifying polyps in vivo in colonoscopy. And there we're working with a language model. So I'm not sure if you've heard about BERT, but it's like a very good language model which can give you sentences like these. So we train it to actually generate more or less sentences in clinical terms so that it can communicate with the medical doctors that actually use those systems. And then lastly, the project that I've worked on most is on esophageal cancer. And I'm going to tell you mostly about this particular project in this talk. But definitely, if you have questions about the other topics, then I'd be happy to answer them later as well. So first of all, a bit of clinical background. So we're talking about this thing called Barrett's esophagus. So here you see, let me get my pointer out. Can you see my pointer? Yes, yeah. I see some people nodding. So in a normal situation, you would have your stomach here, and then it's more or less closed off by a muscle here, and then your esophagus on the top. Well, for some reasons, some persons can develop this Barrett's esophagus because this diaphragm is too wide, and then some acid can flow into your esophagus, and then your body starts replacing these cells. Let me see. By different cell type, and this protects you from getting a lot of infections due to the acid that flows into your esophagus, but you have a higher chance of developing esophageal cancer. So these patients that are identified with such a condition, they regularly go to a community hospital for getting an endoscopy, and then an endoscopist has a look and mostly just takes some biopsies at predefined locations. Then these are sent to a pathologist, and this pathologist will tell whether or not there was cancer found in any of these biopsies. And if no, then people come back after a year or maybe after 2 years. If there is cancer detected, then they're sent to this Barrett's Expert Center. And then if they're early, then they can still endoscopically remove it. And the 5-year survival rate is almost 100% for such a procedure. But if they're late, then radical surgery is required. They need to cut out part of the esophagus, It's a very radical surgery, which also knows a high morbidity, so people will have complaints after the surgery, and also the survival rate is pretty low. And the problem is here in this biopsy procedure that it's very prone to sampling error. So unfortunately, a lot of the patients are only detected at a late stage, also because it's very difficult to recognize visually. So a considerable amount of lesions is not detected at an early stage, leading to a very low survival rate for this type of cancer. So then basically this guy, which you see over here, he's an endoscopist here in Eindhoven at the Catharina Hospital. He basically called our university with the simple question, okay, my phone can detect faces, why can my endoscopy system not detect cancer? And so basically what he wanted is something like this, that we have this AI system telling him this is a suspicious lesion and you should have a closer look or maybe even take a biopsy over there. So then I'm going to do a brief recap on machine learning to make sure that everybody's on the same page. I keep it very high level actually, but I like to bring up this example to make sure that everybody knows what we're talking about. So let's say we want to separate these two types of fruit, lemons from oranges. They have some aspects like color, shape, diameter, and weight. And we want to get some of these aspects that help us differentiate between the two of these. In this case, you would say we're going to use color and shape because they're the ones that are actually distinctive here. So if you would plot these two different aspects, you see that you get a graph where the oranges are mostly in the left top corner and the lemons are mostly in the bottom right corner, right? So this is our training data, and we can model this training data by these two circles. Now we say, okay, mostly the oranges are here on the top left and the lemons are here on the bottom right. So if we now get a new sample, then we can say, okay, it's in the vicinity of most oranges in my training data, so probably this is also an orange. And this is basically what the whole of machine learning, especially classification, boils down to. So you can also see that if you've chosen different features, for instance, the diameter and the weight of these types of fruits, that won't be too much distinctive. And then you get these ellipses that are mostly on top of each other. And yeah, well, if you have a new data point now, the classifiers don't know really what to do. So until mostly the like 2010 and maybe a bit later, what we've been doing is if we get a problem like this where we want to separate two classes, you're going to try to come up with these features that help you differentiate between the two. And then you use a machine learning model after you computed those features to make the decision whether it's an orange or a lemon, or in a clinical case, whether it's cancer or whether it's non-dysplastic tissue. So then based on this machine learning model, you could make a prediction. And this process is called feature engineering. And it's basically what we've been doing for a whole long time, actually. And we try to quantize these aspects. And I also started talking to doctors when I started working on medical problems to ask actually what they're looking for and try to capture that in numbers so I can train a machine learning model with those numbers, or these features, how we call them. Then enter deep learning. Breakthroughs around 2010, maybe 2012 is the most mentionable breakthrough, where you would say, well, basically, I have this data, and I'm not going to define these features, but I'm going to learn these features from the data, and I will have one model that does both this extracting of interesting aspects and making the decisions simultaneously. So there's no clear distinction anymore between these two things, computing aspects and making the classification. So this is also what we've been doing the last like 5, 6, 7 years. And this is called end-to-end learning. So you're gonna basically learn the interesting aspects. In this case, that color and shape is an interesting aspect. You're gonna learn that from the data rather than telling your model that it should use that. So what are the drivers of this revolution? Basically, greatly increased computational power. So here on the right, you see a GPU, a pretty recent one. It's very large. You put this in your computer and you can train these models. And basically, when these techniques were developed like almost or even more than half a century ago, they didn't have this type of compute. And so then also, they couldn't really train them well. And the other one would be very large labeled data sets. So on the left here, you see ImageNet, which is a collection of a huge number of images, in this case, 1.2 million of 1,000 categories. And that really helped training these models. If they had a lot of data, they can learn what features are interesting and what features are not interesting. But you could see that this is a problem for medical imaging because we just don't have this amount of data. So one solution that you could use is called transfer learning. And this is really key in medical imaging. It's used by, I would say, 99% of the people doing deep learning in medical imaging. They're using some form of transfer learning. So you have this, how does this work? Well, you have this data set of dogs and cats and cars and boats, etc. And then you're going to train your neural network. You have plenty of data, so this will work out nicely. Then you're going to transfer this network and you're going to reuse one part of the network and you're going to retrain another part of the network. But because only you need to retrain a small part of the network, you don't need that much data again to do that. So this turns out to work really well. Some of the first breakthroughs in 2015, 16, that really showed that you could do this in medical imaging. So you can transfer the knowledge learned on large data sets. And that's mainly because if you want to discriminate between natural objects, aspects like color changes and lines and patterns in images, that can also be useful for medical problems. So if you have a look around, you can see that virtually all of these systems use convolutional neural networks. So that's a deep learning architecture pre-trained on ImageNet, so on natural objects. And we figured that dogs and cats and cars are probably not the best basis for endoscopic images. So if we want to do esophageal cancer detection working with endoscopy images, probably we can use endoscopy images for that rather than dogs, cats, and cars. So what we did is we collected a very large set of endoscopic images, but we didn't have labels. So we had to train this in an unsupervised way. I won't go into too much detail about this. But we labeled like 10,000 of these images in categories like stomach, esophagus, colon, duodenum, and basically trained it in a partly unsupervised way to have the network first learn how the inside of a human body looks before we would give it the problem of cancer detection, which is a bit more difficult. To go to a bit more in depth about this, so we had several stages of training this model, first with a very large set of mostly unlabeled data, and more we were coming to the data set that we were actually interested in. So you could see that the size of the data set is larger when you start training, but the quality of the data set will increase when you go to your final application. So this is like a multi-stage transfer learning where each time you try to extract some knowledge from a data set and then you move on to a task that is closer to your target task. So in our case, it was esophageal cancer detection. So then where do we stand now at this point? Well, so like I said, we're using this artificial neural network. At this point in time, we have more than 500,000. We're actually over 4 million images that we use for pre-training now, and we've labeled this data set GastroNet, similar to ImageNet, but then for gastroenterology. We use this to pre-train this network, and then we collected a large set of annotations by multiple experts, asked them where in this image do you see cancer, and we use that to train this network. And then basically this network could say to us, okay, I see cancer in this image, and it's approximately here. So there's two functionalities over here. The first one is classifying an image, that there is cancer in the image, and also localizing it so the doctor knows where it should take a biopsy. So to show you some of these results, basically you can see the ROC curve sort of over here, where the optimal point would be over here, where you have a true positive rate of 1 and a false positive rate of 0. And we compared it to 53 medical doctors. So you see the deep learning system of us was very close to the optimal point with respect to like 53 gastroenterologists. So we were very happy with these results, and also very cool to see. There's of course a lot of limitations, and it works very well when you take nice quality images. But this is at least encouraging. And on the right, you can see like some of the heat maps that the AI predicted, also a location for where the doctor should take a biopsy. And you see some of the annotations that were given by experts. So these were really experts on cancer, and those were not the 53 gastroenterologists that basically do these biopsies just out in community hospitals. Then we took this system to the hospital, basically to two hospitals, one in Amsterdam, one in Eindhoven. And we developed this graphical user interface where basically when you take an image, this would directly tell the medical doctor, okay, there is cancer detected in this image and you should take a biopsy over here. And it also showed some confidence score and some uncertainty margin around it. So yeah, we moved to this was the live clinical pilot. You see there was a lot of interest. So there's a lot of clinicians that came to check it out. So it was pretty cool. I'm going to show a brief video of that, but I see that I don't have too much time for this, but then you can get the basic gist of it. So I hope the video runs and you can also see it. So you can see that here in this case, this was like a demo setup where the doctor takes an image, it sends it to our machine, and this directly classifies it as, in this case, non-dysplastic. So there is no cancer in this image. Then if you move to a cancerous case, maybe that's interesting to show. Then you can see that at some point the doctor took an image where we freeze the screen right now, and it was actually detected. And then you can see with a pretty high confidence, so we took a biopsy there. And it was nice to see that the results that we got offline were matched with the results that we got in clinical practice, but still like these procedures were done by experts, so we had very high quality images. Then I'm happy that I arrived at this point in time where I can also, so I have some time left to show you this work, because that's, I think, also very interesting, where we move beyond the visible. So now I've shown you white light endoscopic images, and I've used basically the signals that also a doctor would use. But there are also cases, for instance, in volumetric laser endomicroscopy. This is this device which basically takes an OCT scan, like optical coherence tomography, looking inside the tissue. It has huge potential because you can look inside the tissue, so potentially you could better detect cancer in an early detection, in a very early stage. But the problem is that if you ask your gastroenterologist, he's really not sure, or he or she is not really sure what he or she is looking at. So it's very hard to interpret for human observers. It's also very laborious to inspect because it's a lot of data. So we developed a algorithm that could analyze this type of data. And I think in a more general sense, we will see this more often when the sensors are just producing so much data, and so like data which is more complex than we're used to, or that our eyes are made for, that algorithms can help out there. So I once had this conversation with a medical doctor, and he was telling me that basically, maybe you're not old enough to remember this, but when you had not digital television, but analog television, you could tune your television to a channel that was not existing, and you just see this white noise. And he was comparing this VLE signal to white noise. So he would never start using it without some algorithm that would help him. Then I'm just going to the results directly, and if you want to know more, I can elaborate later how we did this. But what I found interesting of this work is that we can actually find patterns that were very hard for our human eyes to detect, right? So we're completely not good at looking at these grayscale images and picking up on very subtle patterns that elude our human vision. So we can generate these heat maps, and that was telling us that the models were looking at certain layer transitions that we could even hardly see. Also, for example, so on top of these layer transitions, we can sometimes even relate it to the presence of glands or these interesting structures. And for me, that becomes very interesting, where you can actually ask the model where it's looking at. So in this right case, let me get my pointer back. You see that it was really going off on some particularly shaped glands. And we can actually go back to the medical doctors as engineers and ask them, okay, is there something interesting here that we can couple this to? Is there like an anatomical feature that we can relate now to the detection of this model? So that's the main story I would like to convey here, that sometimes these models can pick up on signals that are very hard for our eyes to pick up on. So then I'm coming to the end. So what would I expect that is next? Definitely we are not there yet. So we can do this for very high quality images, but I see a lot of publications that like compare standalone doctors to standalone AI, and I don't think that it's going to work in this way if you actually translate this to the hospital. So we are now focusing on the explainability of algorithms and trying to establish appropriate trust. So having also self-critical AI that can tell the doctor, okay, I'm not really sure about this sample, so maybe you should just not take my advice too seriously. You see a ceiling in the background. It's an interesting example that we had when we just started our live pilot studies, and we just wanted to test the system. So we took an image when the endoscope was not yet inside the esophagus, so it was pointing to the ceiling, and then the our system basically told the doctor that there was cancer in the ceiling, right? So the doctor it was hilarious, and he was not trusting anymore this system because it told him just that there was cancer in the ceiling. But this refers back to this stability, right? The system was never trained with images outside of an esophagus, so it just really didn't know what to do with that. So I think we need to increase robustness, but also efficiency to make sure that you get fast and stable execution across devices and across manufacturers. Then, lastly, we need to start bringing these algorithms to clinical practice, and we need to bridge this domain gap between academic development, like we did ourselves, like using the best clinical available data, very nice images. But then if you move it to some community hospital where they may be less experienced with it, or they're not so focused on image quality, then you see that your nice algorithm that scores very high on high quality data starts breaking down on maybe some more representative data, which you see in clinical practice. So I think that's definitely something that we need to pay a bit more attention to, and that we're actually now starting to investigate. So with that, I would like to again show you some of the faces that were really contributing to this work. And thank you again for inviting me here to give you this talk on the work we do. So thanks a lot. And if there are any questions, please let me know.
Well, thank you very much, Fons, for this very wonderful and interesting presentation you just gave to us. Very delightful to see what you guys are working up there in Eindhoven. Your presentation actually generated a bunch of traffic in our question box in Slido. And I think we still have time for 2 short questions, if you don't mind.
Sure.
So one viewer is asking, thank you, Professor van der Zom, for this nice talk. I see lemons and oranges in a different shape and color now. Could you shortly comment on the fact how you make sure that Denoise data is not giving new features affecting diagnostics?
That's an excellent question. And so we had a recent publication on this. So you see, for instance, people using generative models like GANs or VAEs, trying to denoise images. And there's an interesting example where people used only images of healthy people and then applied it to people with brain tumors. And basically the algorithm was not only denoising, but just also filtering out the brain tumors because it had never seen that before. So that's very dangerous. So I think it's an excellent question. And the way we try to address that is make sure that you understand what happens inside the network. For instance, we are now using techniques from signal processing to make sure we're not basically touching the raw signal and we're only addressing the noise. But it's very hard and it's rather complex, but it's really something that needs a lot of attention. So excellent question.
And then maybe a somewhat related question or follow-up question. One viewer wants to know, well, first of all, thank you. Could you comment on the effort coming from medical device regulations to bring the network to the patient's bedside?
Yeah, so that's also very interesting question. You see a lot of developments and a lot of societies, like in the US, the FDA, but also in Europe and Japan, where we also do some work. They're struggling with how to regulate this, right? Because you can present very high numbers on your own data set, but it's not really a guarantee that it will work in practice. So I think at this moment, there's a lot of good work being done on thinking how to regulate this. And my own personal feeling is that we should involve medical societies. So for instance, I work in gastroenterology. The gastroenterology societies should have their say, and they should think about how to regulate this and to bring it safely to clinical practice, that it will work in all types of hospitals with all types of machinery.
Yeah, that makes sense. Fons, thank you again, once again for your wonderful presentation and for taking the time to answer our questions. And we're happy that you stick around for our podium discussion at the end of this talk.
Yes, thanks a lot again for inviting me, and looking forward to the other 2 talks and see you back after those.
Thank you.
Cheers.
Thank you also for this interesting talk from my side. Now I would like to introduce the second speaker, Felicitas Mungenast. She is a product specialist at TissueGnostics. Felicitas, we are happy to have you here, and we're very much looking forward to your talk.
Thank you. Do you hear me?
Yes.
Super. Okay, let me, I cannot share my screen yet. Now it works. Okay, super. Perfect. Do you see my screen?
Yes.
Yeah, we see it. Wonderful.
Good. So, First of all, I want to thank the YSA team for inviting me to give a talk here. So my name is Felicitas Mungenast, and I am a product specialist at TissueGnostics for actually 2 years now. And before that, I was doing my PhD studies at the Medical University of Vienna in the Institute of Pathophysiology and Allergy Research, where TissueGnostics, tissue cytometry was actually one of the core technology I used for my PhD thesis. And today, I want to give you a short introduction about the company TissueGnostics, our tissue cytometry platform TissueFlux, and the AI-assisted or machine learning-assisted image analysis software StrataQuest, where we have, among other applications, a strong focus on immunophenotyping, spatial analysis, and quantification of the tumor microenvironment in situ. So our headquarters is in Vienna, in the 2nd district. Let me get my pointer. In this very beautiful building here. And we also have subsidiaries in Romania, in China, in Australia, in South Africa, and also in the USA. In 2022, TissueGnostics is celebrating its 19th anniversary. And at the moment, we have actually installations in 32 countries on 6 continents. And we're also happy to announce that by December 2021, we have more than 1,900 reference publications in various application fields. On our website, we also have a very searchable database which contains all of those papers, and it's updated monthly. So if you are interested in tissue cytometry, just have a look at it. So what is TissueFlux doing? So TissueFlux is providing various types of tissue cytometers with which IHC or IF, so immunohistochemistry or immunofluorescence processed samples can be first scanned in bright field, immunofluorescence, multispectral, and also confocal mode. And next, these virtual slides can be analyzed. But I don't want to go to too much detail in the hardware. I really want to focus today more on practical examples of AI-assisted tissue cytometry. So most of you might be familiar with flow cytometry, either from using this analytical method in your work or at least from scientific publications. So flow cytometry has been used for more than 4 decades and can be used to quantify antibody stainings per cell, but only of cells in suspension, like blood or disassembled cells. In opposite, tissue cytometry is the phenotypic and functional analysis of molecules, cells, morphological tissue entities within their native tissue environment. You're doing this by using digitized slides. And it includes the measurements of areas, staining intensities, marker intensities, percentage of marker positive cells, and multiple other parameters. So here are some application examples. So it can be used, for instance, for single cell analysis. So you can assess the marker expression or co-expression between single cells. For the tumor and cellular microenvironment analysis, you can perform phenotypic characterization of cellular subpopulations, also in their spatial context. For immunophenotyping, so you can determine the immune status of tissues in situ. For detailed intercellular characterizations, like structural analysis and determinations of subcellular markers within cells. For the multi-cellular structure detection, so for instance, detection and identification or analysis of blood vessels, glomeruli, tumor, stroma, epithelium, epidermis, whatever you can think of, basically. For the quantification of cellular pathogens, and for instance, including intracellular parasites like leishmaniasis or viral load. So researchers also performed studies with COVID-infected cells using our tissue cytometry platform, HIV, Zika. So as you can see, the application fields are rather wide. And why is tissue cytometry so important? So what you can see here is a column section stained for Ki67, a well-known proliferation marker in brown, and hematoxylin as a counterstain of all nuclei in blue. And the question here is, so how many cells proliferate? So maybe take a look at it and try to estimate a number here. And I can tell you already that we talked with a lot of experts, and the estimations actually ranged between 1% and 40%. And here you can see already a major problem, and this is associated with visual estimations. So what tissue cytometry does is to avoid estimations. With, for example, the single cell analysis algorithm from TissueGnostics, we can segment and detect the cells based on hematoxylin staining and then assess the expression of the markers within those cells. When we analyze exactly that image with our image analysis software, we then get this type of data readout. So on the x-axis, we see the intensity of blue hematoxylin staining. On the y-axis, the Ki67 brown staining intensity. And each dot represents a cell. And the further up the dot is, the stronger is the brown staining. So the higher is the Ki67 expression within this cell. So here we have a cutoff. At here, 14.54% of the cells are Ki67 positive. This was now an example for analysis of one marker, but we can also look at co-expression of multiple markers within cells. So I want to show you now an example of phenotyping of tissue-infiltrating lymphocytes. Here you can see a 4-color experiment. So TAPI is the master channel and the 3 leukocyte markers. What some of you maybe already recognize is that the common marker, so that these 3 markers is actually the common marker combination for deregulatory cells, so CD4 positive, CD8 negative, and FOXP3 positive. So all cells are recognized using the TAPI signal. So the green contours show what the software identified as signal cells. Now we can quantify the staining intensity of each cell in all color channels. So the gate here shows you the CD4 positive cells, and using a backward connection of this gate, we can have a look at the CD4 positive cells directly in the tissue in red. By using the backward connection on the CD8 red marker here, so on the CD8 marker, we can see the distribution of cytotoxic T lymphocytes in our sample. Next, we can also look on the co-expression of these markers, like shown here for CD4, FOXP3 positive T helper cells. And as you may imagine, the complex, and as you can maybe imagine, the complexer the research question, the complexer also these analysis algorithms are getting in the background. But to come back to the actually main topic of this symposium today, AI tools, so machine learning tools, can help us drastically to lessen the workload and to further increase the accuracy of the analysis. And also to make these analysis algorithms for users which maybe don't have a lot of experience in image analysis, to really make them accessible for those people as well. So newest developments in tissue cytometry utilize the power of AI tools. And many of us have heard of AI, so artificial intelligence, from pop culture or Hollywood movies, but these can go mostly gross overestimations or doomsday scenarios. Although AI can in some cases be or become controversial tools, but we are here to discuss AI tools in the context of histopathology. So, what is artificial intelligence really? And where do machine learning and deep learning fall within this category? So here we can see a rough breakdown that shows machine learning is a subset of AI, specializing in self-learning algorithms, which can extract knowledge from data to make accurate predictions. So deep learning is a further subset of machine learning, which leverages multiple layers of artificial neural networks for automated learning and feature detection. But I do not want to go into too much detail here, since I'm not a computer scientist, and I would like to show you again some practical analysis examples that are performed with TissueGnostics high-end contextual image analysis software StrataQuest and its integrated AI machine learning tools. So here you can see an immune organ which is stained for 6 different markers. And this was acquired with one of our instruments. And in total, we acquired 255 individual fields of view, which were stitched together to this nice virtual slide. And StrataQuest has an integrated deep learning algorithm for nuclear segmentation that is especially suited for this type of tissue environments. And why? Because the nuclei in these tissues are very densely packed and are overlaying, especially here in this area, which makes them almost impossible to somewhat accurately detect using classical nuclei segmentation methods. So when we created the deep learning-based nuclear segmentor for our software, we accurately and manually annotated thousands of nuclei in multiple images, just like this one, and then integrated it into a neural network. And to show you the difference between classical nuclear segmentation and also the advantages of deep learning, yes, and to show you the difference between classical nuclear segmentation and deep learning-based nuclear segmentation, here you can see the result of the classical one. The single cells actually are detected nicely, but the very dense areas here made some problems. So we don't have a really nice nuclear detection. Also, the shape is a bit off. And here we were able to improve to use the deep learning-based nuclear segmenter to improve the nuclear detection. And I want to emphasize here that no parameters have to be adjusted or set as it is the case for the classical nuclear segmentation. And this makes the deep learning segmentation much faster. So basically you choose it and you run it. You don't have to make any settings and you get a really nice results. In a direct comparison, you can see that the detection of cells can be improved with deep learning-based method if you compare those two, especially in these very dense areas here, like I said. So what I want to show you next is how easy and time effective our machine learning-based tissue classifier is. So classical algorithms can be very complex, especially when multiple tissue classes need to be detected, as I want to show you here. So here we actually wanted to detect 9 tissue classes in these lymphoid organs. So we want to detect the background, the germinal centers, mantle zones, T-cell zones, epithelium, extratonsillar space, muscle and stroma, and endothelium. And our machine learning-based classifier allows us to segment these different structures based on just literally drawing lines with your mouse on the representative areas on the images for each class. So here the red line, for instance, is for detection of germinal centers. And here we have some lines for detection of T-cell zones. And here, for instance, this yellow line for the extracellular space. And for a sample of this size, we make approximately 6 lines per tissue class. This is, in most cases, already sufficient. So, and by this, actually, you train the classifier. And the next step is just to run it. So you don't need, as a customer who is using the program, you don't need a complex algorithm. You don't need to create a complex algorithm. And here you can see the results of the machine learning-based tissue classification. So you can see the original image, and here you can see it overlaid with a classification mask. So you can really see here in red nicely the detected germinal centers. In yellow, you can see the T-cell zones. In dark blue, you can see the stroma. In violet, the muscle, and so on. And when you combine the nuclear segmentation with this tissue classification, you can analyze the individual phenotypes in their morphological context. So you can look on marker expression, co-expression of markers within the cells detected in the different tissue classes. Now what I want to show you next is how you further can apply our AI tools, or for instance, the machine learning-based classifier. And the next example here includes not the detection of single cells, but of multicellular metastructures of blood vessels. Here you can see a tumor section stain for hematoxylin in blue and the endothelial marker in brown to detect the blood vessels. So this is the original image. What we always do before the analysis of bright field images is to perform a color separation. So this is the unmixed channel for hematoxylin only, and the unmixed channel for the blood vessel marker only. So in green, you can see now the detected blood vessels. Here you can see in blue the detected lumen of the blood vessels. And here you can see the whole blood vessels detected, so the endothelial cells plus the lumen of the blood vessels. Further, we can then use scattergrams by gating, and by gating, like in flow cytometry, differentiate between blood vessels in different sizes. So the red gate is marking now the big blood vessels, which are marked as also in the image now in red. So here we have now the medium-sized blood vessels marked in red, and here as well in red. And here we can see the micro capillaries. So, and this tool also helps us basically to verify the results of our analysis. The last application example that I want to show you is a really nice example for contextual image analysis, where we also use, again, the AI tools. So here we can see a virtual slide of colorectal cancer, and this is stained with 5 markers. So we have DAPI in dark blue, we have the cytokeratin marker, which marks the epithelial tumor in light blue, the CD4 positive cells in red, the FOXP3 positive cells in green, and the KSX7 positive cells in white. And here the question was, where are the CD4 positive cells and where are they located in relation to the epithelial tumor? And I will show you now the automated process of detection, which will lead us to the answer. So what we did first was a classical tissue detection. So we had the tissue class background and the tissue class tissue. The next step was the nuclear segmentation, where we looked at deep learning, where we used the deep learning nuclear segmentation algorithm. And next, by using the cytokeratin marker as epithelial marker, all tumor areas were recognized. And here we can see the epithelial mask in orange. Now we can combine the nuclear mask with the epithelial mask, as you can see here. And we can measure the expression of the markers within each detected cell. But now we want to know how many cells are CD4 positive and in which distance are they located from the epithelial tumor region. So the scattergram here has an input on CD4 positive cells. That means that each dot in this scattergram represents a CD4 positive cell. On the x-axis, the nuclear size is depicted and plotted against the distance in micrometer from the next tumor area. And as you can see, there are a number of gates which contain the CD4 positive cells within a certain distance interval, like 1 to 25 microns, 25 to 50 microns, 50 to 100 microns, and so on. So away from the next tumor area. And here you can already see the statistics. So the total number, that was the total number of CD4 positive cells detected in this tumor area was 7,234. And in a distance of 1 to 25 microns to the tumor, 2,267. In a distance from 25 to 50 microns to 1,593, and so on. And as you can see here, the further we go away from the tumor, the less CD4 positive cells are present. Now we can use the backward connection of StrataQuest to show us the location of the CD4 positive cells within a certain distance gate. So here in red, so what we saw actually in this scattergram, we can also visualize directly in the virtual slide. So here in red, you can see all CD4 positive T cells with, which are not further away than 25 microns from the tumor area. Here from 25 to 50 microns, and here from 50 to 100 microns. Yeah, and here from 100 to 150 microns. And to sum up, we can quantify specific cellular phenotypes throughout the tissue and bring them into spatial context with detected metastructures such as tumor areas. If you are further interested in tissue cytometry, we recently published a review together with collaborators from Queensland University of Technology, Australia, about summarizing various applications of tissue cytometry in research with the main focus on immuno-oncology research. And further, I would also like to invite you to have a look to our website, TissueGnostics.com, where you can find the searchable database for all publications that were utilizing the strength of TissueGnostics tissue cytometry. And with this, I would like to conclude my presentation about TissueGnostics and how you can explore your sample with tissue cytometry with AI-assisted tools. And if you have any questions, please ask now or contact us or visit our website. So I hope I was able to give you an overview of multifaceted functions of tissue cytometry, and I want to thank you for your attention.
Thank you, Felicitas, for this very interesting talk, and we have a couple of questions from the audience. And the first one I would like to start with is, thank you for your great talk. An available program out there that I used for quantitative pathology is QPath. Is this a similar program usable for your questions, and may there be advantages using your programs instead?
Good question. So yes, I think it is comparable. I'm not 100% sure if QPath is open source or not. So what I really want to emphasize here that our software, it's not open source, it's also IVD compliant. So we really undergo very strict audits to, how should I say, to be IVD, so in vitro diagnostics compliant.
All right, thank you. And there is another question. Thank you very much for your presentation. Could you comment on what ground truth you're using to verify the software outcome? Pathologists would need to count all cell nuclei.
Yes, so we have experts who do the ground truths for us. So far we only have a deep learning based nuclei segmenter. So the ground truth for the nuclei was done by experts. And for the machine learning classifier, this is actually done by the customers themselves.
Thank you very much. As there is still time, I would have another question. Is there a limit in the number of markers within a sample that can be analyzed with the TG software?
Actually, no. So usually the limitation is more in the staining of the samples. With StrataQuest, we are able to analyze, I wouldn't say hundreds of markers, because maybe it gets then a bit difficult to really look into the data and get a nice overview. But recently, one of our application experts had a sample with 70 markers, and she analyzed this easily. But in principle, there's no restriction.
All right, thank you very much. Thank you very much for this very interesting talk and having you here in our studio. All the best, and we will see you at the podium discussion in the end.
Thank you so much.
Thank you.
All right, I think all this talking about machine learning algorithms, cell classification, and cancer detection was really tiring, and I think we could all use a short break. You guys can grab some snacks, a fresh beverage, and we'll see you in approximately 10 minutes at 5:05.
Welcome back after this short break. I hope you're all doing fine and you're full of energy again to listen to the third speaker, which is Andreas Handel. He's a former YSA member and now senior machine learning scientist at Kheiron Medical Technologies. Thanks for being here with us today, and we are very excited to listen to your talk.
Thanks a lot. I hope you can hear me.
Yes.
We can hear you.
I'll share my screen now. Can you see my screen?
Yes.
Yeah, it looks good.
Great. So thanks for the kind introduction. I'm very happy to speak today at the Machine Learning in Medical Science, even from the YSA. My name is Andreas Handel, and I would like to start off just with a quick about me. I studied computer science in Vienna, then was working at two big companies, Siemens and Lixto, for a couple of years until I decided to do a PhD in molecular mechanisms of cell biology at the Medical University of Vienna, where I was focusing on microscopic image analysis using AI and image analysis methods. So this was all in Austria. After that, I left Austria and moved to London, where I was working as a postdoc for 4 years at the Institute of Cancer Research. It was also image analysis and AI based, but this time I switched to focus on breast cancer and late stage ovarian cancer. After that, I joined Kheiron Medical, where I'm right now, also based in London, which is a company where we focus on radiological image analysis like mammography or CT. And I would like to start my presentation with some common questions we face in the field when we talk with experts or within the team. There's a lot of hype and fears and myths about AI, and these are questions that I'll often have to answer, or members in my team have to answer when we talk to experts. For example, sometimes people say, am I going to lose my job? Or I can't even get to see a doctor anymore with all these tools around and these AI algorithms that make me redundant. And I can just say, no, that's not the case. First of all, these are tools. They will support you, and final decision-making is still with the expert. So in case of radiology, still with the radiologist. It should speed up your routine work. It should make more time for the patient. Hence, from the patient's point of view, you should see the doctor for much longer because he or she has more time for you rather than spending time on tedious tasks. Sometimes you hear like, I don't do computers. Well, I think that doesn't work anymore, 2022, right? With all these smart speakers and self-driving cars and other tools around like smartphones, that's not an excuse anymore. Sometimes you hear, I know what I'm doing, I don't do change. Well, we're not living in caves anymore, and in medicine, especially, we have made a lot of progress in the last couple of years, or even just if you see the recent COVID vaccine development and that. So there's a lot of change. So that's what life is, right? Last but not least, there's obviously always the worry about data flying around and placing and misuse by our enemies, whatever this is, insurances, other competitors. This has been tackled a lot now with data moving to the cloud. So we have to be very careful where we store data, who has access to the data. For example, we in the company, we keep exact logs of who is accessing what data at what point in time. There's data that's not allowed to leave certain countries, certain continents. So there are lots of measurements now in place to ensure data safety. Yeah. I now would like to go through some very high levels way of thinking in machine learning, because it's not some niche field anymore. It entered the mainstream media. You will find it in newspaper articles and TV magazines and shows. So let's go through some examples. I'll pick something where everybody can relate to. So there's no domain knowledge required, but you can imagine that this task can be also, instead of birds, any kind of medical object that you want to detect. So one flavor of machine learning is, if you would like to call it like that, to identify if a certain object is in the image. So in this case, a bird. So this is a normal classification task where you say, are there any birds in this image? Obviously, there are birds in this image. So yes and no is a binary task. You can say yes, there are birds in the image. On the next level, if you would like to, you can train a model where you actually get to quantify how many birds are in there. So in this case, it's quite obvious. There are 2 birds in there, so the answer is 2. So with a quantification model, you not only get a binary flag yes or no, you would be able to get a number out, in this case, 2. The next level is where are the birds in the image? So previously we knew that there are birds in the images. There are birds in the image. We know that there are 2 birds in the image, but we didn't know where they are. So with localization models, you will be able to say, hey, there are 2 birds in the image and they are at that specific location at the image. The next level is what is in this image? Because there are not only birds in the image, these birds could be in a cage, they could be out somewhere in the woods, they could be on a mountain. So in this case, you would say, okay, there are birds in the image. There is also a branch or maybe 2 branches in the image. We can't say because it's truncated. Something that we face in the normal work too. We not always see everything on the image that we want to see. Sometimes objects are obscured. So that's the next level. And obviously the last one that you could do is like, if you are very stringent and you would like to know for each pixel in the image, so each location, each X and Y position, what does it represent? So there are birds in the image, but there is also a background, right? So there may be grass or forest. We can't really say it's blurred, but we could say for each, we could train a model that says for each single pixel to what class it belongs, where a class could be, let's say, birds, animals, trees, or humans. So machine learning for us is like to study this design of computer algorithms that improve through the process of experience and learning from data. And I'm well aware that these terms are very overloaded because experience and learning can mean a lot to different people. So that's why I would like to go with the previous example through how we can train a machine learning model on a very, very high level. So on the left side, you can see the input image. For deep learning, you normally need loads of them, 100,000 of them, where you have different positions and different birds in there if you would like to train a bird model. That's then fed into a model that's depicted here with this gray box, which will spit out a prediction. The prediction will be, let's say, 0.6 for 60% that there is a bird in there, if that's a binary classification task. You also will need some ground truth labels. Basically, these images will be have to be labeled to tell you what's a bird image and what's not a bird image. And these labels are normally binary, and you would have a 1 for birds in there and a 0 if there are no birds in there. And we then have a function in deep learning where we can compute basically how well we did with the task. And propagate back a loss, that's how it's called in machine learning, to the network to adapt to be better in the next case. And as you can see here, the loss is 0.4. The prediction was 0.6 because it's just, in this simple case, just subtracting from the label the prediction. So over time, this loss will start to decrease until it reaches a very low value, when you basically know in a very simplified way now that you can stop training and try applying this model to new unseen data. So that's on a very high level what happens during training. So when you hear people talking about the training model, that's what's basically going on, going through loads of different examples and thereby showing the model how different birds may look like and in what location of the image they may be present. So what kind of common image analysis tasks are out there? There can be tasks, for example, for an image to classify it into cats or dogs, basically having different categories. Again, for a medical task, this can be people with diseases, people without diseases, for example. On an object detection level, you would be able to train models that do, let's say, box regression. So basically, in this CT scan, you can see here on the left side, the liver has been indicated, or the kidney, or the lung. So basically, you get a box that encapsulates your object of interest. and helps you easily find it. For example, it could also be a tumor. And last but not least, you have semantic segmentation task. This is basically illustrating what I showed with the birds before, where each single location of an image is assigned a certain category. So in this picture above, you can see a group of fishermen on a small river with a boat, and corresponding at the bottom, you can see the corresponding labeled image, where, for example, in this purple color, all the humans are classified, and where the blue color shows the boats, the bright green color, the trees, and the other green, the meadow. So basically, you get for each single pixel an understanding of what's actually representing. So what we do at Kheiron Medical. So we recently released a product called MIA to do recall classification. So we focus on mammography studies where you normally have 4 images. For those of you who are not familiar with mammography, the top 2 ones are sideways projection of the breast, and the bottom 2 images are top-down projection of the left and right breast. And this is what a radiologist normally would look at. In contraceptive screening programs, patients get invited on a regular interval, for example, 3 years interval, to take a mammography screening. And this is then inspected by a radiologist. And if something suspicious is found, we call it a recall. So the patient gets recalled again and undergoes further investigation to see if there's a malignancy or something found like that. And if everything was clear, it's a no recall. So we released a product called MIA, CE marked for usage in clinical practice, where we trained the system on about 1 million of these cases. They were all biopsy proven. I spoke before about labels. Labels are quite important to train. And the better the label is, the better your machine learning system will be in the end. So we had biopsy proven opinions. So we had multiple follow-ups of patients. So we actually knew if that patient developed cancer in the future, because we could look at the previous and the previous scan of that patient, which was very helpful, obviously, to develop a reliable system. The second project I was leading was the MIA IQ, where basically we said we need to develop a tool where we assess the image quality. It's not easy to do the right positioning, and there are many positioning standards out there, but what they all share in common is that the breast has to be positioned in a way that all important regions are visible. So what we did is we interviewed experts in the field, and we went through the different standards, and then trained models that actually segment these important regions in the breast. For example, here in the right side, you can see the blue muscle, the pectoral muscle, and the nipple indicated, for example, in green. And depending on which standard you follow, there are various angles and distances and regions that have to be imaged in order for a mammogram to be a valid mammogram, so that the radiologist can really see all the important regions. So we collected several thousand training levels and trained a system that basically predicts if that scan has to be retaken or not. And as you can imagine, that's quite valuable. First of all, for the healthcare provider, because every retake costs money if you have to come in again and be retaken. But secondly, also for the patient, because if you get recalled into a hospital and your scan has to be retaken, there's quite some burden on the patient, because everybody is then frightened that there may be something wrong with their breast, or it was just a simple positioning error, and therefore the image has to be retaken. So that tool is quite good to assure for quality control of images that have been acquired. I also want to throw in 2 terms, especially what my interest and my research field is, which is the robustness and the reliability. with respect to machine learning. So with robustness, we are concerned about the algorithm's ability to preserve its predictive performance under the variation of the input data. So for example, in mammography, that would mean how stable is the algorithm when we have different scanners, different brands, different models of the scanner. So what you don't want to have is that you develop a system on one scanner and it doesn't translate to the other one, because in hospitals, especially when you roll out at various different sites, and we have 15 sites in the UK and a couple of sites in Europe, where we have our software in the process of being deployed or deployed already. So they all have different manufacturers, and they all have different models of the device. So you need to capture that heterogeneity in the input data to have a system where you can actually trust that output. And the second one is the reliability, where I'm concerning the question whether one can trust the algorithm's output predictions, for example, in a recall or non-recall decision. We look into methods how to quantify if something is, for example, out of distribution, because it could always happen that, let's say, the manufacturer sends in a technician, there's an update to the machine, and that somehow changes the image quality to one way or the other. Hence, the prediction of the algorithm is off because the image got somehow different than it was before. So the system needs to be aware if the image that enters the system is from the same distribution it was trained of, rather than just giving a score which is not reliable, where maybe the radiologist makes its opinion then based on that. And therefore, there could be harm to the patient. So I really would stress that very important for any kind of automated system that it's aware of its limitations, and if the data that's fed is within specifications. So these are two very interesting points and fields in the fields that, especially in industry, we are facing now when we roll out software in the market. And like one of my previous speakers said, in a research setting, you may be able to collect data in a very optimal way. But when you then go to a hospital somewhere in the fields, the data may look very, very different. Or the data may look different because of different ethnicities or different diets or something like that. There's obviously all that can have an effect on the images. So what kind of safety nets are there in AI? In the beginning, so when data is extracted here on the very left side, there are some input safeguards in place here at Kheiron, where we basically check the data that we extracted that comes from the hospital makes sense. So this may be simple checks like the age of the patient, or more complicated checks where you see if there's some consistency issues in the data that you extracted from the hospital system. For the AI algorithms, we look into the robustness and reliability by basically making sure that we capture the heterogeneity out there, basically capturing different ethnicities, different continents, different manufacturers, different software versions, and also seeing if there are any biases in that by stratifying the data. Obviously, you need a lot of data for that, but that's the only way to capture that, right? And the next step, the next safeguard basically for our AI system are output safeguards, where we try to detect failure detection. This can be simple things like that the gray level distribution has changed. So for example, simplified said the images are much brighter than expected or something like that, or oversaturated, if you want to call it that. But that can also be like high level ones where you monitor the, for example, cancer detection rate on the site, and you know how it was for the last 6 to 8 months, and you just spotted a spike in it. So there may be something off, right? So the model may be off because you know what the distribution normally is at that site. And if there's no changes from the population point of view, then it's very unrealistic that you suddenly have a big spike of cancer. So these are important checks that have to be in place to make sure that the environment where you deploy your software is actually safe, because you want to build trust there. And last but not least, you need to have transparency, right? So you need to publish, you need to do retrospective studies, prospective studies, in order to show that your system is really reliable. There are many tools around, but not many make it to the final stage where it actually gets rolled out from bench to bedside, so that it's used in real life on a daily basis. And we are quite happy that we have a product now, MIA, which can be used as either an independent reader or a second reader, and therefore helps the workloads that, especially nowadays, is there with COVID, with the huge backlog of patients who haven't been able to go to their screening, and the lack of radiologists, especially here in the UK, and therefore the burden on the patient who can't go to his or her screening, and therefore is in the uncertainty what's going on there. Yeah, that's it. Thanks a lot for listening. And
Okay, could you comment on the impact of comparability between different X-ray machines? Further, is standardization of X-ray engines important to perform your image analysis?
I can comment on that. I can comment on some interesting observations that we made in the past. There are every machine has a specific fingerprint of how the images look like, so you can easily train a model where you can classify from which machine it comes from. That's trivial. Manufacturers also have specific settings for specific continents, so there are differences between America and Europe, maybe stemming from how radiologists are trained, but that's me hypothesizing. Yeah. There is definitely, you have to use techniques, standard techniques in machine learning, like augmentations, where you try to modify images that they look similar to the other X-ray machine in order to compensate for these biases. Because the big problem that lies there is if you have a shift in your distribution, if you have patients only with cancer patients only from one manufacturer and healthy patients only from the other one, what your machine learning algorithm will do is it will exploit that fact and basically tell every cancer patient has to be from a certain manufacturer. So these are biases that you have to be aware of, and where safety nets in the AI are really important, because you don't want such an algorithm to be deployed at a hospital not knowing that there's this bias in there. So there is currently not a standardization between the manufacturers, and there's a big black box because they don't tell you all about the post-processing, what they do to the image once it's acquired. So it looks quite different.
Okay, I understand. It seems like a difficult issue to tackle. I have one question myself, actually. You've mentioned that for training, you've used labeled data from or labeled by radiologists. How did you get this data? Like, did you have a collaboration and had to pay these guys? And was it difficult for you guys to acquire a large enough data set to train a network?
It's a very, very good question. We have an in-house developed tool that runs on the iPad that we ship to plenty of radiologists who have been annotating samples on a daily basis for the last 4 years. So all the data that I mentioned before was labeled by radiologists manually. We got the data from the hospitals, we got the outcome from the hospitals, the biopsies. So we have like hard proof, like I would call it. If you have a biopsy of the follow-up scan and this patient developed cancer, you can be sure that that patient has cancer. Mm-hmm. And we also have like labeled data where basically radiologists went through, and most of the data is already triple labeled, so that you can actually build a consensus when not even labeled with more radiologists, just to get rid of radiologist biases.
Okay, I see. Thank you very much. So there's no more questions from the audience. So Andreas, we would like to thank you again for your wonderful talk you just gave. And you should also stick around because the podium discussion will start shortly. Yeah, thank you also from my side, Andreas. And yeah, it's time to move to the podium discussion, Philip. Exactly, yeah. So we're going to ask questions to all our three speakers, Felicitas, Andreas, and also Fons. And we want to give you guys one after another the stage to comment on the respective questions. And I would like to start off with a very general one, I would say, and one that maybe also might interest some people in our audience. And that is, so there's a lot of like bad talking about machine learning, that it's all hype and that it's going to simmer down in a couple of years. Do you guys think that it is worth to try to have a career in machine learning, to specialize on it and to apply for jobs, or is it something that's going to be obsolete in, let's say, 10 years from now? Maybe Andreas, you can go first.
I think it's worth going for it. It has served me well the last couple of years. If you know the basics of machine learning and if you get some experience there, you can switch fields quite easily, I would say. It helps obviously have some domain knowledge, especially if you work in the medical sciences. But what we can see right now is that there is a huge demand in the medical sciences for machine learning simply because of COVID. And because of in the UK, for example, because of the lack of radiologists. So healthcare providers have to review images within a certain time limit, and these time limits cannot often be held simply because it just takes too long. And if you, for example, pick the case of CT scans, if you talk to radiologists, how long it takes to review CT scan, especially if there are follow-ups, or if you look at like America, where you have private healthcare, and people come even more often. It's such a time burden to go through that and to compare it with the previous and the follow-up scan. So there will be tools out there that are needed in the future to compensate for the huge amount of data that comes in order to make it feasible for them to process it.
I see. Yeah, makes sense. Felicitas, will you maybe go next?
So for me, this is quite difficult to answer since I'm a biologist and not a computer scientist. So I went in a completely different direction, I guess. But what I can maybe say here is that during my PhD studies, I was working a lot with tissue flux cytometry. So I was doing a lot of image analysis, but actually it was all, I would say, only on single cell level, so I never went into higher dimensions. Also because I didn't know how to do it, so I'm not a specialist in image analysis whatsoever, so I cannot make my own algorithms by myself. And when I realized, so what I actually do is I use tools which computer scientists who are specialized in machine learning create, and I can use them and actually elevate my research. And I think this is pretty cool, actually. So from a biological point of view, I would say, go for it. I need your tools also.
That's a very clear message, I guess. So Fons, for you, maybe I know the answer already, but I just posed the question if it's worth for people to seek a career in machine learning, so to say, or to engage into machine learning research, or if it will be all obsolete in, say, 10 years. What is your opinion on that?
Oh, definitely is worth it, of course. And we need a lot of talented people on the model development side. But I would say the most interesting work, for me at least, is being done at in between the intersection of fields. So like the previous speakers also shown, that if you can apply machine learning to a particular field, you will find that there are challenges there for which you need both domain knowledge on the medical side and the technical side. And for me, that's the most interesting thing. And I think that's more interesting than, for instance, fine-tuning models to score very well in handwritten digit classification, where you see that, the machine learning field is still very active in just these standardized data sets, which is more theoretical rather than applying it to some nice application.
Okay, I see. At this point, I would also like to encourage our audience to post questions in the question box below if you want some questions for our podium guests to be discussed right here on the stage. It doesn't seem to be the case right now, so I'm going to switch to the next question we wanted to discuss with you guys, which is related to regulatory affairs. Since all of you guys work with somewhat deployable applications of machine learning, have you had any issues with regulatory affairs, like in Europe, the MDR, for example? And if you ever stumbled upon these kind of issues, how were you able to solve them? Maybe you guys who work in a company could go first.
Yeah, I'm happy to take that question.
Thanks.
So I'm personally not in the regulatory team, but I was collaborating with that when we went through different certifications and standards that are required in order to grow in different countries or continents. And they require obviously very stringent documentation. And like I started my talk, for example, where I said we need to make sure to log who has access to what and when, which image, which patient has been viewed, has the patient data been anonymized, so you can't really pinpoint which patient it is, and all these kind of processes. So that's quite tricky, especially when you enter a new field or when you extract huge amount of data. This is something, where a lot of eyes are on that. I'm not in that team, but I had to provide obviously documentation code for the machine learning work and how you can provide that it's something safe. So there's a lot of work that has to be done. There's a whole team working on that. Yeah.
I see.
I can maybe add to that from our perspective.
Please.
We also work with companies and see the same thing basically as Andreas just described. But there is like this grayish area, what we've seen before also in recent years, where people working at a hospital capitalize on the data that they collect from patients by, for instance, making a spin-off. There was a huge case for the Memorial Sloan Kettering Cancer Center in New York, where like the director just took all the data and put that into a spin-off. And that's really a grayish area, because this data is like, you really need it to train your models. So it's highly valuable, and basically it comes from patients. And then for me, what I find weird is that in the end, probably these products will be sold to the hospital again, increasing the costs, and then the patients have to pay that while it's using basically their own data. So I think their regulatory issues still need to be addressed. But also, for instance, the thing that I described in pre-training, I still see a lot of models that are taken from internet and then fine-tuned, but they were trained with ImageNet, which is like a public database, and you cannot use it for commercial purposes. Also not as a standard model, but still a lot of people use that, and it's not really enforced yet. But I think as soon as they start doing that, this will give huge issues for a lot of people.
I see. And Felicitas, what is it like for your company, like for TissueGnostics? Do you guys have a lot of trouble with regulatory affairs, or is it something you just came to terms, let's say?
So at the moment we are working on the recertification, since it will come in a few months. It's a lot of work, but I mean, I'm also not really involved, so our QM department is mainly involved into this. But it's a hell of work actually for the whole team, and also we as product specialists or also a marketing team, so everyone has to contribute to it.
I see. And what is your guys' general gut feeling? Do you think that the laws in place are too strict, or are they too low, or are they just right to, on one hand side, keep a balance between patient data safety, but also you guys being able to get your devices into the clinics?
Maybe I can comment shortly here. So our products are not in clinics. So we are at the moment only in research institutes. And actually the regulations are very strict. So really to go into clinics is quite hard work.
And so do you think it would make sense from a law perspective that they lower the bar a bit, so to say? Or is it just right and you still have to, as a manufacturer, just fulfill this bar?
Difficult to say. I think a high bar. I mean, it's about patients' lives, so I think that the laws should be strict. But actually, I'm not. Since I'm not in our QM department, I'm not really familiar how strict it is.
I see.
Not directly in contact with that.
Because there's often complaints that machine learning is basically a black box, and even the people who trained and designed the network don't know what's really going on under the hood. So I think this is a very difficult area, especially for the regulatory bodies of the different states and the European Union to make sure that patient safety is guaranteed and that there's no false diagnosis, so to say. So I think that's a very interesting topic that we all should keep an eye on over the course of the next couple of years. So the next question I would like to ask you guys is more technical. I don't know if I maybe be overshooting with the scope of it, but machine learning algorithms are intrinsically stochastic algorithms, so they're not analytical like some classic algorithms in computer science. Do you guys think that there will be a comeback of analytical algorithms which will be able to solve the problems that we currently use brute force machine learning for? Or due to the nature of the problems, is it simply impossible to find analytical algorithms and we will stick with machine learning? Maybe Fons, you could start commenting on this question, please.
Yeah, it's a nice question, and I know coming out, I've done a lot of control theory as well, where you indeed have analytical models which you fully understand. I said a bit about that, where you really know the model output for inputs ranging from -infinity to +infinity, for example, and can guarantee that stability. And of course, we don't have that when we just train with a subset of data, and then you cannot guarantee the stability. So I think it's a combination of both, because all interesting problems in nature are stochastic, or at least we don't fully understand them, so we treat them as a stochastic problem. But what you now see is, for instance, model-driven approaches where you have some physical model, some physical understanding of your problem, and the things that are very hard, you just put your machine learning elements in there, and you can train the whole thing end to end. Like I said before, by what Andreas also showed, by having these laws and backpropagated through the whole system, but then only updating the AI part and not touching the whole set of equations that regulates your physical understanding. So I think, for instance, also in the sensors, we see this now where you have a physical model of your sensor and then apply AI to do smart sampling, for example. So that's how I see it. I think you need a bit of both, and not fully AI and not fully analytical.
I see. Do you guys have some thoughts on that?
Maybe I can comment a bit. As I said, I'm not a computer scientist.
Doesn't matter.
So actually, with our software, I see the same. So usually we also combine, because some things are quite easy to solve. You don't need machine learning for it. You can just do classical analysis, I guess. So, yeah.
I see.
I agree with the previous speaker. So I personally try to use the simplest way possible to achieve the task. And if that is a linear model, then that's fine, right? So there's no need to train a deep learning model with millions of parameters on it. If something simple does the job, right?
I see. Then maybe as a quick question from the audience in between, this one is actually directed to you, Fons. So the question is, what are the next steps to really get this intersection mentioned by Fons van der Sommen? So I guess it makes sense for you to answer this, Fons.
You mean moving it to the clinic?
I guess so, yeah. If I understand it that way, at least.
Yeah, so I like also that was mentioned by the previous speakers and also by Andreas in particular, that the robustness and the trustworthiness and making it fail safe. So if you only approach the problem from a computer science point of view and you're only interested with input and output data and try to optimize the accuracy, that's not enough, right? You need to think about how will this operate in a clinical setting, and then you need to think about trustworthiness, reliability, but also communication with the expert, like transparency. I think you mentioned this, Andreas. So how does a model come to its decision? So in a certain way, people say it's not relevant, but I think it can help in building appropriate trust. You don't need to fully understand it, but you need to have some better way to communicate it. Because, so let me just give me one brief example. You see, from our own point of view, we were like building models for years, and then we wanted to bring it to the clinic, and we developed this user interface like basically in one afternoon. But I'm now talking a lot with my colleagues from design who are really specialized in human technology interaction. And this is also what you need, and give sufficient attention, right? And not like spending 99% of your time on developing models, but then basically just rushing through the communication with the end user.
That makes sense, I guess. Yeah. There's another question from the audience, which I guess is for every one of you. And the question is, should the future AI research concentrate more on human AI collaboration instead of optimizing AI algorithms alone? What are you guys' thoughts on that?
So from my point of view, I think that, so these algorithms, I mean, you cannot, how should I say? It's the collaboration between, at least in medical research or in medicine, the collaboration between pathologists and AI systems is very important. So I think just having an AI algorithm standing by itself is actually not 100% possible. So I think it should be always assisted. At least this is my impression when we work with customers. I mean, we are more in research, so maybe this is again kind of a different field, but we always recommend to always check the results, because in the end, there can be some kind of mistakes or there can be some failure of the system, and yeah, that's my point of view.
I see. So you really think we should emphasize more on human-AI collaboration instead of solely AI research?
AI assisted.
I see, that makes sense. What are your guys' thoughts on that?
Andreas, you want to go first, or shall I?
Happy to go first. Yeah, I think it's a collaborative effort. I like to challenge that sometimes. So I think last year it was where we generated, where we worked on a paper and published it in radio in the RSNA AI channel, where we used a generative network to generate, if you want to call it like fake or artificial mammography images. So obviously, if you were working like me 4 years with mammography images, you know them. So we said we took up the task that we generate some and then viewed them next to each other, like a fake one and a real one, not knowing which one is the real, which one is the fake. And we showed it at one of the big RSNA, one of the big radiology conferences, and let experts in the field who had like 10 plus years expertise in deciding which one is real, which one is fake, to indicate which one it was. Yeah, they all failed except one. There was one person who picked up on a feature that nobody else picked up. So I like to challenge that, but I think the way forward is a collaboration because none of the parties is perfect.
That is so bizarre. Interesting.
Yeah, so to give, I agree with the previous speakers, and it depends really where you're focusing on. I think we still need a lot of work in AI itself. It's typically a field where the practical side is way ahead of the theoretical side. So I think we need to do some catching up, understanding what actually is happening. But if you want to bring it to an application like in healthcare or medical imaging, then it's really, we need to do way more in integrating the end user with the model. So that's like what Andreas said and Felicitas as well. I completely agree with that. We need to focus on the collaboration rather than the standalone performance.
I see.
Can I add maybe something?
Sure, please.
Just kind of a funny story what happened. One of our workers here, he had a project where he also used some machine or some deep learning network actually to distinguish so deceased patient samples. I think it was pancreatic cancer from non-deceased ones. And so the algorithm worked perfectly fine. It was 100% detected or identified the deceased out of the deceased samples and stated that they are deceased. And in the end, they realized that it was because it was labeled on top and it was written deceased.
That's one way of learning, I guess. Oh my God. Okay, thank you so much.
Verifying results is always important.
That is true, yeah, it's always important. Okay, so another question from the audience states, do you all see potential for neural networks, AI, in emergency medicine? Combining, for example, first fast laboratory findings, clinical data, and e.g. a head or abdominal computed tomography could help to pick out high-risk patients by a sort of risk score. Andreas, you are nodding your head very vividly. Maybe you can go first.
Yes, we have one product for triaging, where you basically go through the data and say which patient has, especially now with the big backlog that the hospitals have, so which are the high-risk patients which have to be seen first because they are the most likely ones to have cancer. And yeah, I think there's big potential there. Yeah.
I completely agree. We're working on this project for people that come in with brain stroke, and then you also want to make a decision directly. They always say time is brain, right? So you want to be as quick as possible to decide whether or not to do some kind of procedure on the patient where you, so it's called a thrombectomy, I think, where they try to fix the bleeding, or whether that doesn't make sense anymore. So in that case also you want to do a very fast risk assessment, and I think AI is perfectly fitted for that.
I guess that makes sense. I guess, Felicitas, you're not so much related to emergency medicine since your company does cell classification, but do you have some thoughts on that, or?
No, I mean, predictive parameters are always super important. So, I mean, I was in cancer research, and it was more about if certain drugs will improve the disease outcome or not. And I guess this is kind of a similar task, a similar question. Yes, so I think that's super important.
Okay, thank you so much. So guys, one last question and then we're going to let you off the hook. We have one from the audience and it actually fits perfectly with what I wanted to ask you guys, which is you playing kind of like fortune tellers and you get to lean out of the window and make wild predictions. So the question from the audience is, what are other topics in other applications of machine learning to be applied in the daily clinic besides diagnostics and H&E stained image analysis? And I wanted to further broaden this question. Like when you look at models like GPT-3, which is like a stupendously large natural language processing algorithm that was shown to actually be able to generate code, and people made fun that now software developers developed an algorithm which eventually is going to drive them out of a job. Combined with the question on where you can see applications in daily clinics, what do you guys see as the future of machine learning in the field of medical science? And you can go wild with your predictions. Maybe we could go for the last round as ladies first, and we're going to give Felicitas the stage.
I'm not familiar with this algorithm. So it's an algorithm that creates code.
So I think I'm not very knowledgeable either, but it's like a large natural language processing algorithm, and they have applied it for all kinds of different tasks. For example, they've integrated it into GitHub as Copilot, where it like auto-completes code and make the job of software engineers easier. And I think there was one application that I saw on the internet where a user could give via their voice some instructions, and the algorithm would code up a computer game. So you wouldn't have to do the actual coding, and the algorithm would just generate it. And like bearing that in mind, do you see anything where machine learning could like make groundbreaking new research, could lead to groundbreaking new research findings in, for example, medical science, our field?
I hope so. So where I see AI in the future is as an AI-assisted maybe diagnosis and predicting tool. So it should go beyond, so maybe which includes all different kind of diagnostics tools, so not only H&E stainings, but also maybe multiple marker stainings, RNA scopes, combines it maybe with, blood samples and detection of other proteins and mRNAs in blood, or and combines all these diagnostic tools or all these samples or the outcomes of the analysis of all these samples into a tool, and then predicts, gives the diagnosis, and maybe also predicts which drug is the best. Yeah.
That sounds awesome. Hopefully someone out there is working on an algorithm like that. Fons, what are your thoughts?
To give my 2 cents, yeah. So obviously there is this care continuum where you could say we're doing not only at the hospital, but also before people arrive at the hospital, monitor them and send the right one to the GP. And so you can, and then also during treatment and after treatment monitoring, you can all have help of AI, obviously. But what I find a really interesting development is, for instance, in molecular science, in drug discovery, predicting what drug will be most effective, what also Felicitas just referred to. There is a huge investment, and now problems are being solved that were open for decades and are now being solved in chemistry and in drug discovery. And that can really speed up drug development, right? If you just can predict what molecule is the best to try next. And I think like graph-based models, but also the language-based models that you just mentioned are excellent in basically predicting what structures will be most effective, but also in a sequence, what's the best thing to do next. So I would say that is a really nice field which is developing rapidly and can really make groundbreaking new discoveries.
For sure. Andreas?
For me, the biggest potential lies in combining different image modalities. For example, we were talking today about histological sections from Felicitas, but also from Fons, from some endoscopic ones, or I talked about mammography and CT. What if you can combine all of that? I mean, the hospital sits on that data, it's in the PAC system, and just think about the sheer potential. If you zoom into the CT scan, you can see an overlay of the mammography registered perfectly there. You zoom in further, you get to the histopathological section that has been taken out of the biopsy, and you can basically get a holistic view where you normally would only get a very small view of what's going on there. I think the combination of that, and that's not even touching genomics that you could put in there. So I think that there's a lot of potential there in the data already that needs to be combined.
I see, yeah, that makes sense. Yeah. If it already exists, why not put it together? Okay, you guys, we're at the end of our podiums discussion. Thank you so much for sticking around. Thank you so much once again for your exciting talks and for taking the time to answer all the questions from us and from our audience.
Well, I also would like to thank all of our speakers who did an amazing job giving us insights into their work. And I would also like to thank the audience who is still patiently sitting in front of their screens and watching this very interesting podium discussion. And last but not least, I want to thank all of our YSA colleagues who helped organizing this very good event. And yeah, with this, I would like to close this colloquium. I wish you all the best. Have a nice evening and please stay healthy. Goodbye.
Bye, you guys. Thank you.